Hi everyone, Dr. Bianchi here, and in this first video, I'm going to take a couple of minutes to walk through the one sample or the single sample t-test problem that we left off in class the other night. I had asked you to work on it during the week and complete it for extra credit points. So I am going to walk through this problem, and I encourage you to do the same. Hopefully you've already taken a shot at completing it and you can see if your answers match up with mine. Let's just first look at the question here. So we have a sample of 16 individuals that are selected from a population with a mean of 80. Notice how we don't have any information about the population standard deviation. We just have the mean score of 80 there. A treatment is administered to the sample, and after treatment, the sample mean is 86. Okay, so it's 6 points above the population mean, and the standard deviation is equal to 8. We want to figure out whether this treated sample is significantly better than the untreated population. Hopefully, if our treatment or our intervention was effective, this group should now be different from the untreated group that they were pulled from. So the first part of the question asks whether or not the sample provides evidence to conclude that the treatment has a significant effect. That's going to be where we're running our one sample t-test and making a statistical decision about whether to reject the null hypothesis, or perhaps we don't have enough evidence to rule out the null hypothesis. Then we're going to back that up with our measures of effect size. We'll be computing and interpreting Cohen's d, the amount of variance explained, and also a 95% confidence interval so that we can estimate where the real population mean would lie had all the individuals been exposed to the treatment. So I'm going to go ahead and I'm going to try something new here now. I'm going to try taking my camera here and showing you the work that I've done on paper. Okay, so just give me a second here. I'm going to hit stop sharing my screen. Okay. Okay, so hopefully this is visible to you. I'm going to zoom out here just a little bit. Okay, here we're running our single sample t-test, and I've just listed the data. We have 16 people in the study. The population mean is 80. After treatment, it's now 86, and the standard deviation is 8. Okay, that's all the info just restated from the question. I encourage you to organize your data that way as well when doing these questions. The first step to computing the t-test is to get the estimated standard error. We're going to use that population standard deviation value of 8 to estimate the error, okay? And that's what I'm going to show you right here, okay? Here we are calculating the estimated standard error. Okay, there's a notation, and it's simply the standard deviation over the square root of the sample size. Standard deviation is 8 over the square root of 16, ends up being 8 over 4, and we get an error term equal to 2.0. Okay, so hopefully for your standard error, you were able to get 2. Make sure you're using the appropriate formulas on the formula sheet for the one sample t-test. Okay, now that we have our error term, we're going to use that in our t-statistic. There is the equation for calculating a t-statistic. Okay, the error term goes in our denominator, and up top is just the difference between the sample mean and the population mean. Well, the sample had an 86, population mean was 80, error is 2, 6 over 2 equals 3. We call this our obtained t-value. Okay, that treated sample has a t-value of 3.00. So now what? Are the results significant or not? Well, we got to consult our table and find the t-critical value. So what is t-critical? Well, let's pull out our t-table. Let's locate 15 degrees of freedom on the left column and scroll over to the 0.05 two-tailed test. And we'll see that our critical t-value is a positive and negative 2.131. That means that our sample either needs to have above a positive 2.131 or below a negative 2.131 to reject the null hypothesis and say that this treatment is effective. Here I've drawn that out visually. Okay, so if we fall in this extreme tail or in the negative tail, we can reject the null hypothesis and say the treatment works. However, t-values in the middle do not provide sufficient evidence to reject the null. A t-value of 3.0 is all the way out here. As a result, we can reject the null hypothesis. The treatment appears to have a statistically significant impact on behavior, symptoms, whatever the outcome variable was. We're confident that that improvement would hold up in the population should they all be treated with this treatment. Okay, so there's your t-test. Now let's go ahead and move into measures of effect size. Let me swap out my sheets here. Cohen's d is the most common measure of effect size. Okay, Cohen's d. And we simply take the absolute value difference between the sample mean and the population mean, and we divide by the standard deviation. Note that sample size has no influence on Cohen's d. That's the whole purpose. Okay, going to give us a pure measure of the effectiveness of this treatment. Okay, we had a 6-point difference between the population and the sample. Our standard deviation was 8. 6 over 8 is equal to 0.75. Cohen's d is 0.75. The sample in this treatment group improved by 3/4 of a standard deviation bracket, okay, medium to large effect. It's pretty hard to push behavior, symptoms, outcomes 3/4 of a standard deviation bracket. Now we're going to go down to R squared. Remember, R squared tells us how much of the improvement does our treatment account for. People improve and get better for lots of reasons. There's lots of variables going on in everyday complex life. Different weather, people are eating different foods, people have different levels of stress. How much of that 6-point improvement can our treatment account for? That's what R squared tells us. We take our t-value and square it, and we divide by t squared plus the degrees of freedom. Our t-value was 3, so we have 3 squared over 3 squared plus 15, okay, using degrees of freedom, n minus 1, and that ends up being 9 over 24, 0.375, or 37.5%. That means that of the 6-point improvement, our treatment accounts for 37.5%, large effect. When we can explain nearly 40% of anything, especially complex human behavior, symptoms, emotions, etc., that's pretty good. Now, what about this confidence interval? We introduced this last class. Let me just zoom out here. A confidence interval is going to tell us where does the true population mean lie. Yes, this sample had an 86, but had the whole population been exposed to this treatment, what would the mean be? Okay, the formula is to take the sample, or to take the population mean, excuse me, and to that add and subtract the critical t-value associated with the degrees of freedom times the estimated standard error. Up top, I've done the mean of 80 plus 2.131, that's t-critical, times the error 2, and I get a value of 90.262. That's the upper limit of my confidence interval. What's my lower limit? Okay, an eraser on here, see if I can get that off. Okay, the lower limit is going to be 80 minus 2.131 times 2, 81.738. We can be 95% confident that if the entire group was treated, okay, the entire population, that the mean would be somewhere between 81 and change and 90. Okay, this is the t-value associated with a 95% confidence. Now you can compute other confidence intervals, 80% confidence, 90% confidence. You always use the critical t-value for the level of confidence desired. Okay, so that's walking through an entire t-test. Go ahead and get my camera back on there. That's walking through the entire one sample t-test. Okay, walking through how to compute it, make a statistical decision, and then compute all three measures of effect size, Cohen's d, the amount of variance explained, and confidence interval. Okay, any questions on that, post to the discussion board. I'm here to help, and I'll see you in the next video.